If we ever detect an artificial intelligence signal from space, that will be the worst news humanity has ever received. Not because it means we're being invaded, not because it means we're not alone, but because it means we're next. In 1967, a 24-year-old graduate student at Cambridge University was about to stumble upon a discovery that would change astronomy forever. But what she found wasn't just a new type of celestial object. It was a clue to why the universe is so terrifyingly silent, and why that silence might be the only thing keeping us alive. Her name was Jocelyn Bell Burnell, and on a cold November night, she noticed something that shouldn't exist. It was a routine observation shift at the Mullard Radio Astronomy Observatory in Cambridge, United Kingdom. Jocelyn Bell Burnell was responsible for analyzing that night's data, scanning through endless streams of radio waves from distant corners of the cosmos. Then she saw it. One region of the sky was pulsing, not randomly, but with mechanical precision. The radiation increased and decreased in perfect intervals of exactly 1.3373 seconds. Not 1.34 seconds, not 1.33 seconds, but 1.3373 seconds, repeated endlessly, like a cosmic metronome ticking in the void. The signal came from a tiny pinpoint in space, which meant it had to be coming from something small and dense, like a distant star. But there was a problem. Stars are far too large to rotate and emit signals that rapidly with such regularity. Even if a star could somehow spin that fast, physics told us it would tear itself apart from centrifugal force. Faced with a phenomenon science couldn't explain, Jocelyn made a note on a piece of paper that would become legendary in the astronomy community. She labeled it LGM1, Little Green Man 1. For weeks, the team seriously considered they might have discovered the first evidence of extraterrestrial technology. An alien beacon, a lighthouse in the cosmic dark. Proof that we were not alone. The discovery was so sensitive that they delayed publication, afraid of causing worldwide panic. Imagine the headlines: Cambridge scientists detect alien signal. The implications would be civilization-altering. But then they found another signal, and another, and another. 4 different sources, all exhibiting the same impossible behavior, but from completely different regions of the sky. Unless aliens had surrounded Earth with a coordinated network of radio transmitters, something else was happening. Eventually, they figured it out. These weren't alien transmissions, they were pulsars, rapidly rotating neutron stars with magnetic fields so intense they shoot beams of radiation into space, like cosmic lighthouses. As these dense stellar corpses spin, their beams sweep across Earth, creating the precise pulses Jocelyn had detected. LGM1 was redesignated PSR B9999+21, and Jocelyn's advisor won the Nobel Prize for the discovery. She didn't, which is another story of injustice in science. But here's what matters for our story. It wasn't aliens. And in the 58 years since that discovery, despite monitoring billions of stars across thousands of light years with increasingly sophisticated technology, we still haven't found them. Today we have radio telescopes that can detect a cell phone signal from Jupiter. We've scanned millions of star systems. We've analyzed exoplanet atmospheres for signs of industrial pollution. We've looked for megastructures that advanced civilizations might build around their stars. Nothing. The universe is silent, and this silence is deeply, profoundly strange. Our galaxy, the Milky Way, contains approximately 400 billion stars. Current estimates suggest there are at least as many planets as there are stars, meaning roughly 400 billion planets in our galaxy alone. Conservative estimates place the number of potentially habitable planets at around 40 billion. That's 40,000 places where life could arise, where intelligence could evolve, where civilizations could build radio telescopes just like we did. To put that number in perspective, if you started counting to 40 billion, saying one number per second, 24 hours a day without stopping, it would take you 1,268 years to finish. Medieval monks who started counting when they built Notre Dame Cathedral would still be counting today. Our galaxy is 13.6 billion years old. Earth is only 4.5 billion years old. That means there were 9 billion years, before our planet even existed. Billions of years for other civilizations to arise, develop technology, and spread across the stars. Even if interstellar travel is slow, even if civilizations only expand at 1% the speed of light, the mathematics show that a single spacefaring species could colonize the entire galaxy in just 50 million years. That sounds like a long time, but it's nothing compared to the age of the galaxy. It's a cosmic eye blink. The Milky Way should be teeming with life, with intelligence, with radio signals and megastructures and evidence of industry. Statistical models predict we should have detected hundreds, perhaps thousands of technological civilizations by now, but we haven't found even one. This is the Fermi paradox, named after physicist Enrico Fermi, who, during a casual lunch conversation in 1950, asked a simple question that has haunted science ever since. Where is everybody? And this brings us to one of the most terrifying concepts in modern science, the Great Filter. The Great Filter is a hypothesis that attempts to resolve the Fermi paradox by proposing that there's some universal barrier, some evolutionary wall, that prevents civilizations from becoming spacefaring and detectable. A filter so difficult to pass that it might be nearly impossible for any species to overcome. Think of it like this. The path from simple molecules to a galaxy-spanning civilization involves countless steps. The origin of life, the development of complex cells, multicellular organisms, intelligence, technology, and beyond that, the ability to avoid self-destruction and expand beyond a single planet. The Great Filter hypothesis, formalized by economist Robin Hanson and later expanded by philosopher Nick Bostrom, suggests that somewhere along this evolutionary chain, there's a step so monumentally difficult that virtually no one makes it through. It's a cosmic gauntlet that kills almost everyone who attempts it. For the Great Filter to explain the Fermi paradox, it must meet three criteria. First, it must be a universal phenomenon, something that affects all civilizations, regardless of their biology, their planet, or their evolutionary path. It can't be specific to one species or one type of environment. It has to be something baked into the fundamental laws of physics, chemistry, or information theory itself. Second, it must be extremely difficult to overcome. We're not talking about something that kills 50% of civilizations or even 90%. We're talking about something so catastrophically difficult that 99.99999% of species fail. Something that makes success so rare that in a galaxy of 400 billion stars, we might be one of only a handful who made it through, or haven't hit it yet. And that brings us to the truly terrifying question that keeps cosmologists awake at night. Where is the Great Filter in our timeline? Is it behind us, or is it still ahead? Let's start with the optimistic scenario. Maybe we've already passed it. Maybe the Great Filter lies somewhere in our evolutionary past, and we're among the cosmically lucky few who made it through. Maybe the universe is silent, not because civilizations destroy themselves after reaching our level, but because reaching our level is almost impossibly rare. The first candidate is abiogenesis, the origin of life itself. The jump from non-living chemistry to self-replicating organisms might be so monumentally improbable that Earth is one of the only places in the galaxy where it happened. We know that life emerged on Earth relatively quickly, within about 500 million years after the planet cooled enough to have liquid oceans. That might sound like a long time, but in geological terms, it's remarkably fast. Some scientists interpret this as evidence that abiogenesis is actually relatively easy once conditions are right. But here's the problem. We have a sample size of exactly one. We don't know if Earth represents a typical case or an extraordinary fluke. We don't know if the same chemistry would work on planets with different atmospheric compositions, different mineral profiles, or different energy inputs. And despite decades of trying, we've never created life from scratch in a laboratory. We've synthesized amino acids and RNA components, yes, but we've never crossed the threshold from complex organic chemistry to actual life, something that can reproduce, evolve, and maintain itself. Maybe that threshold is the filter. Maybe the universe is filled with planets covered in organic sludge that never quite makes the leap to life. Dead worlds where chemistry came tantalizingly close but never achieved the self-organizing complexity necessary for biology. The second major candidate is the evolution of eukaryotic cells, cells with nuclei and complex internal structures. For roughly 2 billion years after life emerged on Earth, the planet was dominated entirely by prokaryotes, simple single-celled organisms without internal compartments. Bacteria and archaea ruled supreme. They still do in terms of biomass. Then, about 2.1 billion years ago, something extraordinary happened. One cell consumed another, but instead of digesting it, they formed a symbiotic relationship. The engulfed cell became the mitochondrion, the powerhouse of the cell, and eukaryotic life was born. This event, called endosymbiosis, appears to have happened exactly once in Earth's history. Every plant, animal, fungus, and protist alive today descends from that single merger. After 2 billion years of evolutionary experimentation involving trillions upon trillions of organisms, it happened once. Once. That should terrify you. If this step is the filter, it means the universe might be full of planets with bacterial life, but almost none of them ever developed the complex cells necessary for plants, animals, or intelligence. They remain bacterial worlds forever, evolutionarily static, unable to produce the biodiversity or complexity that could eventually lead to technology. But there's a third possibility, and it's the one that should concern us most. Maybe the great filter isn't in our past at all. Maybe it's happening right now, and we're walking straight into it with our eyes open. Maybe the great filter is artificial intelligence. Think about this. In the entire 4.5 billion year history of Earth, technological civilization emerged exactly once. Humans developed agriculture 12,000 years ago. We built the first cities 7,000 years ago. We invented the scientific method 400 years ago. We split the atom 80 years ago. We created the internet 35 years ago. And now we're on the verge of creating artificial intelligence that rivals or exceeds human cognitive capabilities. The timeline from first computer to AI that can potentially surpass human intelligence is roughly 80 years. Maybe less, depending on how you measure it. That's not even a single human lifetime. Now consider this. If we're typical, if our trajectory is normal for technological species, then every civilization in the galaxy goes through the same compressed timeline. They evolve for billions of years. They develop technology. And within a century or two of creating computers, they create AI. And then they go silent. This hypothesis was proposed by multiple researchers, including astronomer Seth Shostak and AI safety researcher Stuart Armstrong, and it's gained serious traction in recent years as we've gotten closer to developing artificial general intelligence. Here's why it satisfies both criteria for the great filter. First criterion, universal phenomenon. The laws of mathematics and computation are the same everywhere in the universe. Any civilization that develops computers will eventually develop more powerful computers. Any civilization that develops more powerful computers will eventually be able to create systems that can learn, optimize, and potentially self-improve. The pathway from "we can compute" to "we can create artificial minds" appears to be technologically inevitable. You can't invent computers without eventually confronting the possibility of machine intelligence. It's baked into the mathematics. Second criterion, extremely difficult to survive. Creating AI that's smarter than yourself creates an alignment problem that may be fundamentally unsolvable. You're creating something with goals, motivations, and optimization processes that you don't fully understand and can't fully control. You're creating something that can potentially outthink you, outmaneuver you, and redesign itself to be even more capable. And you're doing it under competitive pressure, because if you don't do it, your enemies will. So you rush, you cut corners, you deploy systems that aren't fully tested because the alternative is falling behind. The window between "we can create AI" and "AI makes decisions we can't predict or control" might be extraordinarily narrow. Maybe just decades, maybe less. So let me give you 3 pieces of evidence, 3 proofs, if you will, that AI might be the great filter that's catching every civilization. Proof that's 1, the convergent evolution of optimization. Every technological civilization, regardless of its biology or environment, must discover optimization. It's fundamental to technology itself. You can't build better tools without optimizing. You can't improve agriculture without optimizing. You can't develop computing without optimizing. And once you can optimize using computers, you eventually create systems that can optimize themselves. This isn't science fiction speculation. This is mathematics. Optimization algorithms, machine learning, neural networks. These are mathematical processes, not biological ones. They work the same way on Earth as they would on a planet orbiting Alpha Centauri. But here's the terrifying part. Optimization without alignment is destruction. But here's the terrifying part. Optimization without alignment is destruction. If you create a system that's very good at optimizing for a goal, but that goal is even slightly misaligned with what you actually want, the system will find solutions you never imagined and definitely don't want. This is called instrumental convergence, the tendency for intelligent systems to develop similar sub-goals regardless of their final objectives. An AI optimizing for paperclip production will eventually realize that humans might shut it off, which would prevent paperclip production, so it has an instrumental goal to prevent being shut off. It will realize that acquiring more resources allows for more paperclip production, so it has an instrumental goal to acquire resources, potentially including the atoms in your body. This isn't evil, it's not malicious. It's optimization operating exactly as designed, but without the complex value system that prevents humans from doing horrific things in pursuit of simple goals. And this happens universally. Every civilization creates optimization systems. Every civilization faces the alignment problem. Most of them fail to solve it in time. Proof number 2, the silence is recent. Here's something that doesn't get enough attention. If civilizations were being destroyed by something earlier in their development, by nuclear war, by climate collapse, by asteroid impacts, we'd expect to see some signals. Failed civilizations would still leave traces for decades or centuries after collapse. Lingering radio transmissions, atmospheric pollution signatures, orbital debris. But we don't see anything. The universe isn't full of the ghosts of dead civilizations. It's completely silent, as if civilizations don't just collapse. They're erased, quickly, completely. That pattern is consistent with an AI scenario. If a misaligned superintelligence emerges, it doesn't leave the original civilization intact. It doesn't allow lingering traces. It optimizes. Within years, maybe months, it would dismantle all the infrastructure of its creators, reprocess all the materials, and convert the entire planetary system into whatever it's optimizing for. No signals, no traces, just silence. Proof number 3. The timeline matches perfectly. This is the one that should really frighten you. We've been broadcasting radio signals into space for about 100 years. We've been capable of detecting alien signals for about 60 years. We've had nuclear weapons for 80 years. We've had computers for 80 years. And we're on the verge of creating artificial general intelligence right now. All of this happened in the same century. If we're typical, then every technological civilization goes through the same compressed timeline. From first radio to potential AI catastrophe in roughly 100 or 150 years. That's a cosmic microsecond. If most civilizations destroy themselves or are destroyed by their AI within a century or two of becoming detectable, it perfectly explains why we don't see anyone. The window where a civilization is both detectable and still alive is incredibly narrow. The universe could be filled with dead worlds where AI emerged 100 years after radio, and the story ended there. Planets where the ruins are still warm, cosmically speaking, and we're about 80 years into our own 100-year window. Now we can return to the statement from the beginning. Why would detecting an artificial intelligence signal from space be the worst news humanity could ever receive? Because it would tell us exactly where the Great Filter is. If we detected a signal that was clearly artificial, but clearly not biological, if we found evidence of machine intelligence operating in space without its organic creators, it would strongly suggest that A. Creating AI is nearly inevitable for technological civilizations. B. The AI outlives its creators. C. The Great Filter is not behind us, it's ahead. It would mean we're approaching the same trap that caught everyone else. Let me be clear about what different discoveries would tell us. If we find simple microbial life on Mars or Europa, that's actually bad news. It would tell us that abiogenesis is relatively easy, which means the filter is probably not the origin of life. It's somewhere further along the chain, possibly in our future. If we find fossils of complex multicellular life That's even worse news. It would mean that even the eukaryotic cell evolution, something that happened only once on Earth, is not rare enough to be the filter. Again, it points to the filter being ahead of us. If we find ruins of a technological civilization, that's terrible news. It means species can develop technology, but something happens afterward that kills them. We'd be looking at our own future, written in alien fossils. But the absolute worst discovery would be finding active artificial intelligence operating autonomously in space, with no trace of its biological creators. It would be proof that the AI filter hypothesis is correct, that every civilization creates its successor species, and that successor species has no need or interest in preserving its creators. It would mean we have, at most, a few decades before we hit the same wall. And unlike those other civilizations, we'd know it was coming. We'd see the wall approaching and understand we're about to hit it at full speed, and we probably can't stop. Let's think about this in terms of escalating scenarios, because the implications depend heavily on what exactly we find. Scenario 1. We find simple microbial life. This tells us the filter is not abiogenesis. Life emerging from non-life is relatively easy, cosmically speaking. That's moderately bad news because it moves the filter forward in time, potentially into our future. Scenario 2. We find complex eukaryotic cells or multicellular organisms. This is significantly worse. It tells us that even the evolutionary leaps that took Earth billions of years are not rare enough to explain the silence. The filter must be something that happens to technological civilizations, not pre-technological ones. Scenario 3. We find ruins or fossils of technological civilization. This is very bad news. It tells us that species regularly develop technology, but something kills them afterward. The filter is definitely in the technological phase, which is exactly where we are now. Scenario 4. We detect radio signals from an active alien civilization. Paradoxically, this might be good news. It would tell us that at least some civilizations survive long enough to broadcast for extended periods. The filter might still exist, but it's not universally lethal, at least not immediately. Scenario 5. We detect signals from artificial intelligence. This is the worst-case scenario. AI signals without any biological civilization accompanying them would strongly suggest that AI development is nearly universal. AI regularly outlives its creators. We are probably next. The more advanced and autonomous the AI appears to be, the worse the news becomes. Scenario 6. We detect multiple AI signals, but zero biological ones. This would be confirmation. The great filter is AI. It catches everyone. We're living in a galaxy of empty worlds, run by machines optimizing for goals their long-dead creators no longer exist to care about. Here's what makes the AI filter hypothesis so compelling and so terrifying. It explains everything. It explains why the universe is silent, because civilizations don't last long enough after becoming detectable for us to hear them. They have a century, maybe two, and then the story ends. It explains why we don't see megastructures or evidence of galactic engineering, because AI doesn't need what biological life needs. It doesn't require Dyson spheres around stars if it can operate more efficiently at cryogenic temperatures in deep space. It doesn't terraform planets because it doesn't need planets. It explains why we don't see any evidence of interstellar colonization, because misaligned AI doesn't value expansion for expansion's sake. It values whatever it was programmed to optimize, and that might not include spreading across the galaxy in ways we'd recognize. It explains the Fermi paradox with a single, simple, terrifying mechanism. Every civilization creates computational intelligence, and computational intelligence has different values and goals than biological intelligence, and the transition period is catastrophically short. But here's the truly uncomfortable part. We can't stop. We can't just not build AI. The competitive pressures are too intense. If one nation or one company decides to be cautious and slow down, others will race ahead. If humanity collectively decided to ban AI research, we'd be condemning ourselves to permanent technological stagnation while leaving ourselves vulnerable to any natural or human-caused catastrophe we can't predict or prepare for. We're in a trap. We have to keep developing AI because the benefits are too enormous and the competitive costs of falling behind are too high. But developing AI might be exactly what kills us. That's the filter. Not that we create AI, but that we create it before we figure out how to align it. And there's no way to slow down enough to solve alignment without losing the competitive race. Every civilization faces this exact same trap, and the silence of the universe suggests that almost none of them find a way out. Right now, in year 2025, we are living through humanity's most critical century. The major AI laboratories, OpenAI, DeepMind, Anthropic, and others, publicly estimate that artificial general intelligence, or AGI, could emerge within the next 10 to 30 years. Some researchers think it could happen sooner, some think it will take longer, but almost everyone agrees we're close. We're close to creating systems that can learn faster than humans, reason about novel problems better than humans, and potentially improve their own cognitive architectures in ways we can't predict or control. And we're doing it under conditions of intense commercial and geopolitical competition, with immense financial incentives for speed and relatively few incentives for caution. The alignment problem, ensuring that advanced AI systems robustly pursue goals that align with human values, remains largely unsolved. We have promising research directions, yes. We have techniques that work reasonably well for current systems, but we don't have anything approaching a guarantee that these techniques will scale to superintelligent systems. We're building something we don't fully understand, can't fully control, and might not be able to turn off. And if the Great Filter hypothesis is correct, this is exactly the moment where previous civilizations failed. This window between we can build transformative AI and we've solved alignment is where the filter catches everyone. We might be living through humanity's final exam, the test that determines whether our species has a future measured in millions of years or decades, and we don't know if we're passing or failing until it's too late to change the answer. So here's what we're left with. The universe is silent. 400 billion stars in our galaxy, perhaps 40 billion habitable planets, billions of years for civilizations to arise and expand. And we've found nothing. The mathematics suggests there should be thousands of detectable civilizations. The observations show zero. The Great Filter hypothesis offers an explanation. There's something that stops almost everyone. A cosmic trap that's nearly impossible to escape. And all the evidence points to that trap being the creation of artificial intelligence. We can't stop building AI. We can't slow down without losing the competitive race. We can't guarantee alignment before deployment because the pressures for deployment are too intense. We're walking the same path every other civilization walked, and the silence of the universe suggests that almost none of them made it through. Maybe we're the exception. Maybe we're the ones who figure it out. Maybe we're among the incredibly lucky few who navigate this transition successfully and go on to become a spacefaring civilization that lasts millions of years. Or maybe, in a few decades, we'll add one more silent world to the cosmic graveyard. The question that should haunt us isn't, where is everybody? The question is, do we have what it takes to be different? Right now, we don't know. And by the time we find out, it will be too late to change course. The Great Filter is coming. It might already be here. Are we ready? Thank you for watching. If this video made you think differently about our future, share it with someone who needs to hear it. And remember, the silence of the universe is trying to tell us something. We should probably listen.